Uh, okay, I think it's recording. So, all right. So today's crash course on vectors will be quite a long one, but hopefully I can speed things up by skipping over some of the calculations and stuff like that lah. So the main point of this crash course is just to, well, one thing is that a lot of students who are taking H2 math always complain about how vectors is a difficult topic or there's a lot of things to remember. So what I want to do for today's crash course is really to just organize the different concepts that are in vectors, as well as try to help you guys visualize and form some intuition on how to think about vectors so that it's not as scary as most people you know most people think it to be lah, right? Okay, so I think I've mentioned to some of my students that for vectors, usually we split it into three parts, right? So vectors part one will just be on vectors when you talk about things like dot product, cross product. Then parts two and three will be on lines and planes. But I think for revision, okay, I think the most important part of these three is the first part, right, for vectors. So I want to slow down for this first part so that we can really dive into the visual intuition on vectors before we talk about all these like different examples on how to apply things like your dot product and cross product to solve problems involving lines and planes. Because after all, lines and planes are really just kind of like case studies or examples, if you want to put it that way. Those aren't really the main bulk of your, shouldn't be the main bulk of your revision lah. Okay, so let's start off with vectors. Let's just do a quick recap on vectors, just assuming that perhaps you might have forgotten, maybe like secondary school vectors and stuff like that. So some basics, right? Of course, for the first part, let's talk about how we denote vectors. Okay, these are very, very basic stuff. So we can denote vectors in a few ways. The most common way, or the most common two ways, are usually the first one with a bold-face letter, right? Usually lowercase letter. The second one is just this notation where you have an arrow on top, right? Okay, so the last one is going to be the simplest. This basically just, let's think of it as okay, vector BC. We read it as vector BC, but I want you to think of it really as a vector going from B to C. That's exactly how we write it, right? B to C. Okay, so this is what essentially what our understanding of vectors is. Vectors bring us from one point to another point in Euclidean space, like XY plane, XYZ space, right? Okay, so I will use all of these notations quite interchangeably. Sometimes, if the situation calls for it, I will use this capital letter version. If not, sometimes I'll just talk about, I'll just type it out as a bold-face letter lah. Okay, but just to point out, when you write a vector using this first notation, of course we don't do this. We don't make the letters bold. Okay, so to make it bold, we just write the letter usually normally, and then we just put a tilde underneath. If you're extra lazy like me, you can just underline it. It doesn't really matter. Okay, so this is just how we denote vectors. Just a recap lah. Okay, so now on to the visual intuition for vectors. Okay, so Usually how I explain vectors to students who are seeing it for the first time usually are secondary school students, but nevertheless, okay. So let's think of vectors as sets of instructions. Instructions on how to move from point to point. Let's say I want to talk about, okay, let's go back a little bit further. Okay, in secondary school, we learn things like coordinates on your XY plane, right? So what are coordinates? Coordinates are a way to describe position, right? Back then, we talk about position in XY plane. Now we talk about position in XYZ 3D space. So positions or points, right? Now we want to build this new object called a vector, which will bring us from point to point. For example, let's say I want to talk about how to move from origin, which is usually the default reference point. How do we travel from point O, origin, to this certain point A, which has this set of coordinates? So coordinates are kind of like addresses, right? And vectors are instructions on how to travel from address to address, okay? So this is quite simple, but let's point out a few properties or a few things that we need to understand about vectors before we dive into some of the more complicated stuff. So over here, you can see 3 different vectors. So green color, blue color, red color, okay? So for the green part, what we are illustrating is exactly what I just mentioned, that vectors are instructions on how to move. For example, from O to A, right? So vector OA, okay, this is a position vector. Okay, so be careful of things like, for example, A, 2, 1, 2, this is coordinates. Okay, these are coordinates, right? Okay, OA, vector OA, which is equals to this, we write it as a column vector usually, so like this. This is a position vector. A position vector essentially is just how to get to this place or this point A from our origin, from our reference point, okay? So coordinates, position vector, although we sometimes, you know, as students, we kind of like mix them up a little bit, that's fine, okay? Just make sure you know what is the correct term for it, just in case the question asks for, let's say the question asks for coordinates, so you can't answer the question with a position vector and vice versa. Okay, so the green part illustrates that a vector is kind of like an instruction on how to move from point to point, specifically, or rather particularly in this case, from O, origin, to point A, which has this set of coordinates. Okay, now this blue vector, okay, I will use this blue vector to illustrate that I can, in a sense, decompose a vector into multiple vectors. Kind of like how I can decompose a set of instructions to someone, okay, into smaller instructions that are easier to follow, for example, right? Okay, let's say I want to talk about how to travel from point A to point B, okay, exactly where this blue vector takes us. Okay, one way to think about it is that I can describe this set of instructions by telling someone that, okay, you know where the origin is. So you're going to go back to the origin, then find your way to B because you know the coordinates of B, right? So you know how to get there from origin, right? Likewise, you know how to get from origin to A, and therefore you know the way back to the origin. So I can decompose this vector AB into 2 vectors, okay, AO plus OB. I typically don't like how, you know, I think some teachers, they teach you how to write vector AB as OB minus OA. I don't really like it because I need to memorize something. Yeah, I don't like to remember. I don't like to memorize stuff. So the easier way to think about it is So just now I mentioned that I usually think of this vector AB as vector that takes me from A arrow to B. What that means is I can write it as from A to O, then from O to B. And this is how we decompose vectors, or at least how I like to think of it, right? And then now I know that AO, okay, vector AO is simply negative OA, which is kind of like the opposite instruction, right? If I tell you how to move from O to A, then A to O is just kind of like walking backwards, undoing the action. Okay, so we can express vectors as a linear combination of other vectors. Okay, in a sense, this is just decomposing a vectors into different parts, right? Okay, why linear combination? I wouldn't really talk much about it. Simply, it just means you can add a bunch of vectors, but before adding, you can just scale the vectors by some number, like for example, -1 in this case. Okay, but we'll talk a little bit more about these. Okay, we won't really talk more about this because it's quite simple, but we will see a bit of this when we go through some examples. Okay, now the more important part, I think, is the red part. So if you look in this diagram, right, we have a green vector, we have this blue vector that we talk about how this takes us from point A to point B, but how I figure out, okay, for example, let's say I erase this, okay, so let's say I erase this. Now if I want you to find I want you to find vector AB. How you will do that is you can think of it as walking from A to O, then O to B, and then you do this set of workings to get vector AB. Now, the interesting thing, or the useful thing about vectors is that if you think of vectors as a set of instructions, then I can kind of recycle the instructions in a way. In a sense, recycle, I mean we can use a set of instructions to, let's say I tell someone a set of instructions that takes them from point A to point B. I can tell someone else, maybe at point C, the same set of instructions, and they can follow it to get to this other point D. Okay, so these are equal vectors. Okay, these are equal vectors. So when I was a student, when I was studying for H2 math, this concept, although I think it's quite simple. I think most students should know how this works. But I think the notation can make things a little bit confusing, right? For example, why would I call this red vector AB? It doesn't take us from point A to point B, right? That kind of makes a little less sense, right? Because vector AB tells us how to, that's the instructions on how to walk from A to B. So this shouldn't be AB, but we need to remember that vectors are kind of like instructions, and therefore we can copy paste instructions elsewhere so that we just recycle them. Basically, we just call this vector CD. That's the same thing as vector AB, just that we can apply anywhere we want. Okay. Okay. So these are just kind of some basic ideas, right? So let's move on to some important stuff. Okay. These are some things that, although we might have seen in secondary school, maybe E-math, but we are dealing with 3D vectors now. So I think it's best for us to go through some explicit examples with numbers. Okay. So one very important thing, okay, if I want to simplify the idea of vectors, right? Vectors, for people who study physics, might think of them as arrows, right? Okay, we visualize them as arrows that point a certain way with a certain length, right? A vector precisely has magnitude and direction. These are the two very important things about vectors that we must keep in mind. Okay, I know it seems a bit too simple, and I don't think people really think about this that much, but it's very important that we remember these two things. Vectors only give us two pieces of information. First one is the magnitude, which is kind of the length, and the direction where it points. Okay, so let's talk about magnitude first. To get the magnitude of a vector, you simply use Pythagoras theorem. But Pythagoras theorem, you need to apply it twice. Okay, I won't show it here because I don't think it's useful. It just looks like applying Pythagoras theorem. Okay, so a vector, if you want to find its magnitude, all you do is you take the x, y, and z component, you square each one of them, you add them up, you square root it. Okay, simple enough. These are three examples with numbers. I hope I typed them out correctly. Okay, if you see any mistakes, you can just drop me a text or something and let me know. But these, you can read through them on your own. I don't want to spend too much time on these. So magnitude of a vector, very simple to calculate. Okay, we will need to use them quite often, but just keep in mind that magnitude of a vector is one of two things that a vector can tell us. Okay. Now, to talk about, okay, so I mentioned vectors have magnitude and direction. Okay. The direction part is it's a little bit more confusing than the magnitude part. I can't exactly, like apply a formula, right? Like Pythagoras theorem or whatever, right? I can't apply some formula to extract the direction of a vector. So how can I use, or how can I get something that can denote the direction of a vector? The direction of a vector is preserved by, it's stored in a unit vector. Okay, a unit vector is essentially the same thing, just scaled to unit length or length of 1 unit. Okay, so for the purposes of I'm not gonna read this out, but you can look at how we can get a unit vector for, let's say, a vector S. Let's say I have a vector S that points in this certain direction and it has a certain magnitude. Okay, so this is vector S. Okay, this is vector S. It has a certain magnitude, which is called, which is the modulus of vector S. If I want to describe this vector's direction, what I do is I just divide the vector, or rather I scale the vector. Okay, I divide it by the magnitude. Okay, this gives us a unit vector that preserves it preserves only the direction. Only the direction. Okay, this is important because sometimes we only want the direction part of the vector. I don't care how long a vector is. Sometimes I just want the direction of a vector, right? So by simply just dividing by the magnitude, we preserve the direction, we throw away all the information about the magnitude. Okay, so this is very, very important. Okay, I can't stress enough about how these basic concepts are so important for vectors, the three topics in vectors. Okay, so again, I put some examples here. If you spot any mistakes, you can let me know, but I won't really go through the numbers here because they are quite simple. Okay, but of course, just to point out, usually when we divide by the magnitude, we get a bunch of surds, we get a bunch of square roots. So if you key in your calculator, usually you get a bunch of decimals, right? Because of surds, irrational numbers. right? So a quick way to, let's say I don't want to count, for example, like square root of 77, or sometimes maybe even square root of like 100 something or a few thousand, right? I don't want to like think about how to simplify the surd, right? The easiest way you can do that is just on your calculator. Let's say, for example, let's just pick maybe, let's say, this one, okay? It's because the numbers are quite small. So let's say I don't know, okay, you know what? Let's do vector C, okay, because the numbers are uglier. So let's say I do this vector. I want to find the unit vector that preserves the direction of vector C. So what I need to do is I just need to divide the vector C, okay, by its magnitude. So magnitude of vector C. Okay. To do this, I simply just multiply the vector. Okay, so let me just copy down the vector C. So vector C is 3/4 -2. Okay, let me write it like slash, okay, and then half. So I have a vector C here. I'm going to divide this by the magnitude of this vector, which is simply, okay, let me just put it as 1 over something. Okay, so I divide by square root of, and then I square every component. I square each component, sorry. Okay, let me make some more space. Okay, so square root of the square of each component, and then I add all of them up. And then I square root the whole thing. Okay, so this will give me the unit vector C hat. Okay, so let's say I don't want to count all these, right? Maybe the numbers, I don't want to deal with numbers, right? So what I can do is type it into the calculator, but you will run into some issue because the calculator won't give you inserts. I don't think it does that. So a quick and easy trick is to type this thing into the calculator. So type this, okay, then square it. Okay, or well, just don't do the square root. Okay, just square it. Okay, then you go and manually square root that thing, so that you don't get a bunch of decimals, right? Okay, this seems a little bit silly to say, but just in case, okay, just if you type into the calculator, please don't round off. Don't just see like a bunch of decimals and then you round off. Don't do that. It's a square root. Just leave it in surd form. Okay. 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 Enough nagging. Let's go on to the next part. So, okay, just so that we wrap things up, we previously just talked about how vectors have magnitude and direction. Okay, you can get the magnitude of a vector by applying something that looks like Pythagoras theorem. Okay, for the direction of a vector, you can extract the direction of a vector simply by finding the unit vector in the same direction, or dividing the original vector by its magnitude. Okay, these are two pieces of information we can get from a vector. We will usually use, I would say we only use these two pieces of information, but we are going to deal with these two pieces of information with things like your dot product and cross product, okay, which we will cover a bit later in about two pages. Okay, now let's talk about simpler things that we can do to vectors before we talk about the products. Okay, we can do two main things with vectors: scaling a vector and adding vectors. Okay, this is going to be quite similar to how in graph transformations you can scale and you can translate or shift, right? So same for vectors, we can scale we can translate or shift, scale and shift. Reflecting a vector is just it's a negative vector, but it's simply scaling a vector by -1. Same as how you would think of graph transformations, when you scale by a negative number, the graph flips. Okay, so again, a few examples to illustrate how to deal with these numbers. But scaling a vector is simply just, for example, if I want to multiply a vector by a certain number lambda, right? I just multiply component-wise. So every component just gets multiplied by lambda, and that's it. Okay, next part. Negative vector is just scaling by -1 or multiply by -1, which means all of its components will just flip sign. If your components are, for example, in this case, positive, positive, and 0, then it will flip to negative, negative, 0. Just multiply -1 to every single component. Okay, but our understanding of it is that the vectors will flip direction. So from this direction, it flips to the opposite direction. Just like how we mentioned in the above diagram over here, right? When we talk about how to find a vector AB that takes us from point A to point B, what we can do is decompose it into AO plus OB. AO is created by scaling vector OA by -1 or flipping the vector. That's a negative vector. Okay. So again, I think these are quite simple, still secondary school stuff, just with one extra dimension. So now, next one that is from secondary school is vector addition. Vector addition, you just add component by component, right? So for example, if I want to add 2 vectors, I just add up the x's, add up the y's, add up the z's, put them back into the vector, we're done. For subtraction of vectors, you're just adding the negative of the second vector. Okay, so some explicit examples over here. I won't talk about these numbers, so let's just move on. Okay, so vectors have magnitude and direction. I know I'm very naggy, but this is very, very important. Vectors have magnitude and direction, right? We can get the magnitude by doing something that looks like Pythagoras theorem. The direction of a vector is obtained by dividing the vector by its magnitude. Okay. Afterwards, we talked about how we can scale vectors, which is simply multiplying all components by whatever number you want to multiply by. Flipping a vector or finding a negative vector is done by multiplying every component by -1. The last thing that we just talked about is how we add or subtract vectors. We just add or subtract them component-wise. Okay. Now let's talk about the important stuff, right? These last two things that we can do with vectors will be elaborated upon, or rather it'll be used in the rest of the vectors trilogy, if you want to call it that way. So we have 2 ways of taking or finding products of vectors. Okay, unlike numbers, which we just multiply, vectors, we need to define how we take these products. It looks like multiplication, but we need to be precise which way we are taking the products. So before we look at the formulas or whatever you want to call it, let's draw some pictures. Let me add a page because I forgot to add some space for diagrams. Let's try to gain some visual intuition on what a dot product and what a cross product does. Okay, so I'm going to put them side by side, but I'll talk about dot products first. Okay, but before that, let's also mention the names. Okay, dot product is written as a dot. Okay, so for example, vector A dot vector B. Okay, but a more useful name that we usually don't use that word because dot is easier. It looks exactly like the symbol. Another name for it is scalar product. It's a bit more useful because it tells us or it reminds us that this dot product or scalar product, A dot B, gives us a scalar. Okay, this is a scalar. It is a scalar quantity, number basically. Okay. Now cross product. Okay, same thing. Cross tells us the symbol, right? Or it's literally the symbol is a cross, or what we write as like times. Okay, so a cross product, another name for cross product is vector product. This is a bit more useful because it reminds us that whenever we take a cross product of two vectors, that gives us a vector. Okay, which means it has magnitude and direction. It's not just a number. Okay, so this is going to be important. Okay, I'll just foreshadow a little bit. This will be important for things like your zero vector, for when you encounter zero vectors. But otherwise, not super important yet. Okay, just be mindful that whenever you have things like, I'll talk about it later, but when you get things like zero vectors, just be careful. It's a vector, it's not just zero, so you need to put a tilde underneath. So like this. Okay, let's focus on dot product first before we talk about vector product or cross product. So dot product is going to be, you need to be able to visualize dot product in a way that is helpful, right? In introducing the dot product, I almost never ever tell students the formula or what it's equals to, like the something cosine. I'm not going to talk about that yet. Let's only talk about the picture before we talk about any mathematical formulas or whatever calculation you can calculate with these two products. So for dot product, okay, I will first throw a bunch of words first. Okay, the dot product is related to ideas like projections. Okay, projections and the property of things being parallel. Okay, or as I like to usually call it, similar instead of parallel. Okay, so this is a little bit more, this would mean a little bit, this would be a bit better appreciated by maybe H2 physics students. So in H2 physics, usually we can decompose a vector into its, let's say, X component and Y component, right? So we can, for example, let's say vector V, we can decompose it into two parts. The X component of vector V, okay, and the Y component of vector V. Okay, so why do I mention that dot product is something to do with the idea of parallel, being parallel, or why does it have to do with similarity, right? Similar. Okay, the dot product can sometimes be used to talk about how much a vector is similar to another vector. So let's throw this aside. It's not very useful. It's just to just for the physics students who find this a little bit familiar. Okay, the concept of vectors being similar can kind of be explained by, let's say, just drawing two arrows. Let's say I have this arrow and, okay, maybe I use a different color. Let's say this arrow versus maybe this arrow. Okay, let's say this arrow. Okay, so these three arrows, you can kind of tell that even without any calculations or even without any knowledge of what vectors really mean, you can ask a kid and they might tell you that vectors or these two red color and blue color arrows look quite similar, right? They point in roughly the same direction. They have roughly similar magnitudes or lengths. Okay, but the black color vector is pointing elsewhere. Doesn't seem to be very similar to these red and blue vectors. So vectors, dot product of vectors tell us how similar vectors are or how much vectors agree with each other. How to use this to our advantage is simply just, let's say somehow I can find the dot product of these vectors. Let's say the red vector, let's just call red vector R. Okay, then black vector will just be B. Okay, let me maybe change this to green so that they have different letters. Okay, so this is the green vector, this is the red vector, this is the blue vector. Okay, so let's say somehow I know how to calculate the dot product. So R dot B versus, let's say, R dot G, right? These two dot products. Okay, somehow I know how to calculate them. Whatever the answer is, okay, whatever the answer is, it somehow tells us how similar vectors are. It tells us how close to being parallel they are. Okay, so I want you to bear this in mind when we go and calculate or when we go and evaluate what dot products are, right? Okay, now let's talk a bit about projections. Projections, you need to really understand it visually. So let's just draw a picture. How I usually think about it is a little bit gross, but let's say I have this vector, this red color vector. Let's say this is a mosquito, okay? Mosquitoes are usually black. So let's draw a black mosquito. Okay, so let's just call it this vector M, okay? Now, how I usually think of it is I like to think of projections as like killing mosquitoes, okay? So if I want to kill a mosquito, okay, let's say the mosquito is flying somewhere. Let's say this Apple Pencil is a mosquito, right? It's flying somewhere. I want to kill it. Usually what I need to do is I need to clap my hands together, make sure the mosquito is stuck in between my hands, right? So let's say, how am I going to hold this? Let's say the mosquito is like this. I hope you can see it. Okay, so let's say the mosquito is like this. And if I want to kill the mosquito, I slap the mosquito into my hand, into my palm, right? Okay. Something like that. Okay, so let's say my palm is here, this dotted line. Right? That's the surface of my palm. And I slap this vector down with another hand. Okay, so I'm just gonna put like maybe a rectangle or something. So I use this other blue color hand to slap this mosquito vector down into my red color palm. What I'll get is this mosquito will be squashed like so. Okay. This is a bit gross, okay, but I think it's, yeah, but if it's gross, then I think it will be easier to remember, so hopefully it helps, okay? So I think of projections as slapping a mosquito into a palm, for example. So let's say I position my palm along this red color dotted line, I will get this squashed mosquito. If I position my palm in a different way, for example, maybe let's say the green colored way. Okay, let's say I position my palm in this green color way. And then of course, if I want to slap the mosquito down, I have to slap. I can't use this blue color rectangle anymore, right? I need to use, for example, let's say like this. I need to slap it, like sandwich it, right? I can't slap diagonally, you know, I can't, yeah, okay. So that's how you kill mosquitoes, right? You clap your hands together. So when you clap this orange color hand into your green color palm, what you get is a mosquito that is squashed like this. Because it collapses, right? It's like, pretend this is a long mosquito. It collapses into just a little dot on your hand, right? So this is my way of visualizing projections. It's a little bit gross, but it helps with just, well, one thing is that it's gross enough for me to remember it well. Second thing is that this is oftentimes a good way to talk about vectors, at least, or visualize it in your head before you do any calculations, right? Okay, so notice how in these two examples, when I slap this black color mosquito, let me just erase the palm. When I slap this black color mosquito into two different palms, okay, two different, let's say, orientation of my palm, okay, I get two different squashed mosquitoes. I get this, let's change it to blue. I get this blue color one, and I get this orange color one. Okay, notice how the blue color mosquito, or the blue color remains of the mosquito, is more, seems like there's more mosquito collected on my palm, as opposed to that orange color one. Sorry, I just pointed at my screen, I don't know why, but this orange color one that is very tiny, or it's kind of like just a dot. It's like the mosquito was quite long, right? This vector mosquito, right? It now became kind of like a dot. So the reason is because projections tell you how similar your vector is to the direction of your, say, your palm. If you slap a mosquito that's, let's say, this long vector mosquito, right? Let's say this mosquito is sitting on my palm like this, and I squash it. The mosquito will just be like that, but flat. So I retain quite a lot of the mosquito, right? The mosquito looks exactly the same. It's still long. But if the mosquito is standing like this, and I slap it like this, the mosquito becomes a dot. Okay, I don't know if you can see it, but yeah. So just, yeah, okay, just a dot, right? So the idea of how similar vectors are is kind of encoded in this visual understanding of projections. Okay, this will be, again, a little bit, this will again be very useful when you talk about things like length of projection, or projection of vectors on lines or planes or whatever later on. Okay, so bear these pictures and these words in mind when we talk about other things. Okay, now let's talk about how to really evaluate a dot product, right? So when we do a dot product, when we squash a mosquito, we need a few things, okay? First of all, let's be very precise with the language. Not legit language, but more of the language we use in our head when we think about vectors, okay? When we do a projection, we are not projecting a vector into a, you shouldn't think of it as projecting a vector onto something else. You should think of projecting a vector into a certain direction, okay? I am not projecting a vector. For example, I'm not squashing the mosquito into, okay, I don't think this analogy is going to work out if I keep using the mosquito example, but let's just try to take out the important parts of this analogy. Okay, so whenever we project a vector, let's say I want to project this, again, this black color mosquito vector, okay, I can choose the direction, okay, to squash the mosquito. So for example, I want to squash into this palm, then I slap it this way, okay, then the mosquito will collapse. I can choose another orientation. Maybe I want to move my palm angle a different way, and then I have to slap it this way, for example. Okay, so you always talk about projections with respect to a direction, not a line per se, not a plane per se, just the direction or kind of like the surface in a sense. You want to think about it that way. Okay, we always project into a direction. You only need a vector and a direction to do a projection. Okay, very important. So what I mean by a vector and a direction is like this. Let's say I have a vector M and I have this direction represented by this red color dotted line, right? I'm going to project my vector M by squashing it downwards into this dotted line. Okay, and the mosquito that gets collected on this red color dotted line will be here. Okay, I draw like squiggly lines to show that it's kind of like squash lah. Okay, I preface this by saying that it's going to be quite disgusting. Okay, so when I squash a mosquito, let's say the head is this arrow of the vector. It makes sense that when I squash the mosquito, the head should be pointing that way as well. And indeed, the vector gets pointed this way. The head is still there. Okay. Okay. Now, okay, so let's bring in some math into this. Okay, instead of just talking about mosquitoes. So a projection is done by using a vector M, for example, dot, which projects. Okay, dot is the projection. Yeah, it's just the projection product, basically, right? So M dot, and then I choose a direction. Remember that just now I mentioned how we talk about directions in the context of vectors. Directions are encoded in a unit vector. So M dot, let's say this red color one is, let's say, vector N hat. N hat describes the direction. So M, vector M dot vector N hat. Okay, maybe I change the letter so that it's easier to read. So maybe use it as a D or something, direction. Okay, M dot D hat. Okay, this is called a projection. When we have this projection, we can do things like, okay, we can later on do things like, for example, modulus this. Or for example, maybe I can, let's say, try to find the angle between them, right? Again, let's wait till later, then we talk about the more complicated stuff. But the idea is that this M dot D hat is the projection. Later on, we can talk about things like length of projection, projection vector, or acute angle between two whatever things, right? Okay, but this is called the projection. Okay, let's be very, very, very clear about this. Okay, now from here, from this picture, let's extract some information. Let's draw out this. We can kind of see a right angle triangle here. Let's draw it out first. So we have a right angle triangle here, and the hypotenuse is where the vector lies. So the vector is over here, okay, vector M. Okay, so let's call this angle theta. Okay, and then what we can see is that when we project, okay, so let me also draw the vector d hat. So vector d hat. Okay, so I'll draw the vector d hat a bit smaller because I don't want you to think of it as like d hat is not the palm that you're snapping into, right? D hat is not the palm. D hat is just describing the orientation of your palm. The direction is the only thing that matters here. So when you slap vector m into this direction d hat, okay, which we will continue drawing with some dotted lines, okay, what we get is this bunched up mosquito, right? This bunched up vector. Okay, this is called the projection, and you can use simple trigo to find out what this thing is. Okay, so using trigo, using some simple trigo. Okay, using some simple trigo, right? We can write down that this thing, okay, I'm a very slow person, so I'm going to take it step by step, okay? So usually I see a right angle triangle, the first thing I do is that the adjacent to the angle or the opposite to the angle or whatever, right? In this case, it's adjacent and hypotenuse, so we have cosine theta. Cosine theta is going to be that bunched up stuff over the normal arrow, right? Okay, let's not use pictures, let's name it something. Okay, so remember that I said this bunch of stuff is called the projection. The projection, okay, this thing is called the projection. Okay, this projection is m, okay, vector m dot vector d hat. Okay, that's a projection. So let me just also write it down over there. Vector m dot vector d hat. Okay, now what is the hypotenuse? The hypotenuse is vector m, right? But we can't really divide by a vector, so let's just modulus it. Okay. So this is our right angle triangle. Using trigo, we get this, right? This tells us a few things. This tells us, for example, okay, I'm just going to go off tangent a little bit because over here we can see a few concepts ahead of the sequence that I want to cover. So the first thing is we can find the angle theta. You can find the angle theta by doing cosine inverse of that, whatever that is. Okay. If you feel like this looks a little bit different from what you see in your notes, that's because it might not be an acute angle, right? Because I didn't really modulus the whole thing. So later on, we'll talk about the nuances of this, whether we need to modulus it or not. Okay, but this gives us some angle. This gives us some angle. Okay. Now the next thing is that over here, let's move the modulus m over to the other side. So we get vector m dot vector d hat equals to modulus of m cosine theta. Okay, this still doesn't really look like your dot product formula. Okay, so it's kind of like a little bit off on both for both of these two things, right? So let's think about what the differences are. Okay, let's talk about this one first. So the difference is that typically when we do dot product, we don't always dot a unit vector. We usually just dot the vector itself. So let's say m dot d instead of m dot d hat. What is d hat? D hat is just vector d divided by its magnitude. So let's just pretend the magnitude is over here, and then we just multiply it to the other side. So what we get is modulus of vector m modulus of vector D, and then cosine theta. This is what you should be familiar with. This is your dot product formula in a sense. Okay. So by just using this weird mosquito analogy, okay, of thinking about it, we get the equation or this formula for dot product. Okay. Doing this weird kind of like roundabout way where it's a little bit more confusing can help us understand a bit better and remember these formulas or these concepts a little bit better, right? Because we have to work a little bit harder to get back something that usually people just memorize. So we need to understand a bit more intuitively what these operations are doing, what these objects are. Okay, so this, I really stand by this way of thinking about vectors because it really takes us all over the place. Okay, so all of the concepts they will see later is simply just using a bunch of these things that we are going to talk about. Okay, we're going to see most of the things right now. Then afterwards, we are just using these tools to solve different problems. Okay, let's look at this other one. It's a little bit off, right? It doesn't really look like what we are used to. Usually we have a big modulus here instead of a bracket. Okay, the reason why is just that this theta could be obtuse. Let's say instead of the vector D pointing roughly the same direction as vector M, right? Let's say vector D is instead pointing some other direction. Maybe let's say vector D is this. Okay, so let me draw it slightly different color. So like this. And then now I have vector D hat over here. Okay, so vector D hat is kind of like pointing somewhat the opposite direction, right? Looks a little bit pretty different from the black color vector. So the angle between them is obtuse. Okay, obtuse. So let me just write down here, obtuse. Okay, instead of using, okay, I'll just use theta, okay? So we don't see too many different symbols. Okay, so this angle is obtuse. What happens when we get an obtuse angle and we are going to do like, let's say trigo with obtuse angles? We should recall that in secondary school, we have a bunch of like trigo, I guess it's not really identities, but more of like just trigo properties that you usually memorize. I don't want you to memorize them, okay? But we need to remember that for cosine, let me sketch out the cosine curve. For cosine, the curve looks like this, right? This is cosine. So cosine theta, this is theta. Okay. Okay, so cosine. When your angle is obtuse, okay, so let me draw the dotted line here. This part is acute. Okay, let me draw the cosine curve a little bit fatter so you can see more clearly. So let's say like this. Sorry, looks very ugly. Okay, like this. Okay, so let's just say we have our cosine curve here. This is pi over 2. Over here is in the acute region. Over here, that's pi. This is obtuse. When we have cosine of an acute angle, it's going to be positive. When we have cosine of an obtuse angle, it's negative. Okay, so when we do cosine theta, and theta is acute, we get a positive number. When we do cosine theta and theta is obtuse, we get a negative number, right? We can't do cosine inverse on a negative number, right? In secondary school, you learn about things like principal value and what you can put into the inverse trigo functions. Let's not talk about those things now. Just if you type into a calculator, your calculator tells you something is wrong. Okay, so something is wrong. So what we need to do is we need to take modulus of this thing to take care of the fact that when it's obtuse, cosine theta will be negative. Your calculator doesn't like it. Okay, so you take modulus before you find your angle so that your angle is always acute. That means, let me change this theta. Okay, let me change this theta to, let's say, alpha or something, some other symbol. And theta is still the same place. So whenever we want to find an angle, we usually want to find the acute angle rather than the obtuse angle, because there's always going to be one acute, one obtuse, unless it's right angle. So we just pick one to focus on. And by convention, we focus on the acute angle. So how to get the acute angle? You simply modulus this thing. Okay, so let me actually just write this in a different color. So this modulus, so the modulus or the absolute value, okay, modulus forces the angle theta to be acute. Because by convention, we just ignore the obtuse part. Of course, if you don't do the modulus, you go and do your cosine inverse. Actually, I'm not very sure whether the calculator likes it or not. I'm under the assumption that the calculator doesn't do, let me check, cosine inverse negative number. But usually I don't like to use the calculator, so I'm not very sure. Okay, so let's say negative 0.5. Okay, turns out the calculator can handle that. So I guess it's fine, but okay, nevertheless, let's just always only talk about the acute angle. If you want to find the obtuse angle, just draw a picture and then 180 minus the acute angle to get the obtuse angle, or pi radians minus theta to find the obtuse alpha. Okay, so I will rehash all these formulas that you need to know, but this is just building up all of these things simply by using this analogy of projecting a vector into a certain direction, as well as using some simple trigo and some algebraic manipulations. Okay, now let's go back to here. Okay, so dot product. Let's go back to these two words, projection and whether something is parallel or similar. Projection is what we call this thing. When we slap this mosquito down, that's called a projection. The projection is vector m, or the mosquito vector, dot the direction vector. Okay, sometimes maybe the direction is pointing somewhat like in the opposite direction, not really in the same direction as the mosquito's head. In that case, our projection will be negative. Okay, that ties into the idea of how a dot product talks about similarity. Because when it's very similar, when they are pointing in roughly the same direction, the dot product will be positive. When the dot product is negative, when the projection is negative, that means the two vectors are dissimilar or roughly anti-parallel, pointing the other direction. Okay, so let's draw a few pictures to write this down, to note this down. So if your vectors are pointing somewhat in the same direction, okay, let's say this is a vector A, vector B, then in this case, vector A dot B is going to be positive. On the other hand, when your vector A is pointing that way, but your vector B is instead pointing kind of the opposite way, right? Kind of the other way, right? Rather than something like this. So they are very different, right? As opposed to this, kind of looks like they are roughly pointing somewhat the same direction, right? This is like almost opposite direction. So dissimilar. So your dot product is going to be negative. Dot products, positive dot product tells us that the vectors are similar. Okay, I use inverted commas because this is just a way to build intuition. It's not a proper way to talk about vectors. Now, if your dot product is less than 0, when it's negative, you say that these vectors are dissimilar. Okay, we think about it that way. Now, what happens if in between? What happens if your dot product is equals to 0? That means it's neither here nor there, right? Your vectors aren't really pointing in similar directions, neither are they pointing in dissimilar directions or opposite directions. They're just at right angles to each other. Okay, they're just right angles to each other. Okay, so this is going to be an important say property, I don't know what to call it. This is going to be an important thing for us to remember because we will be using this fact to show that two vectors are perpendicular. Okay, so this is going to be important. Okay, so this is a bit messy, okay, and I apologize for this, but throughout this pretty messy journey, we see that dot product gives us a lot of ideas that will be covered in the following concepts throughout vectors, lines, and planes. Okay, that's why I want to slow down and really cover this in detail. As messy as it seems, I'm sorry because I'm not sure how to make this a bit more organized because it's really like kind of like a mind map is jumping all over the place. But I hope that this introduction will make things a little bit, or hopefully a lot easier when we cover the many different concepts. Okay, now let's talk about cross product. Okay, so for dot product, we visualize it or we think of it as projections, right? Kind of slapping a mosquito into a certain palm, a certain direction. Now, cross product, you can think of it in two ways. Okay, I will talk about this in two ways, and they are both going to be useful. It's just that one way, I don't think that you would have seen this unless you study physics. So, vector product, okay, one way to think about it that is not really related to this projection thing. Okay, so let me just perhaps, okay, let's see how to arrange this. So vector or vector product or cross product, two ways to visualize. Okay, so one way to visualize is going to be quite similar to how we talk about projections. So let me just draw like a dotted line here to show that in this one corner, I'm going to talk about a slightly different way to visualize cross products. Okay, so this other way to talk about cross products is extra visual, okay? Sorry, not exactly lah, but yeah, okay, I'll just point it out first. When you do a cross product, let's say vector A cross vector B, vector A cross, let's do a different color, vector A cross vector B. Okay, what you're doing is you are sweeping from A. Okay, let's say A cross B. So let me just write down first. A, I don't like to use black for the vectors. Let's use red for the vectors. Okay, so red vector A, I'm sorry, let's change it to R for red. Okay, sorry. Okay, R for red. Vector R dot cross vector B. Okay, cross vector B. When we do a cross product, we are sweeping from the first vector, vector R, to the second vector, vector B. So you should think of it as this. Okay, it still looks somewhat similar, like because I draw the arrows like that. So this picture and this picture, you have a bunch of arrows, but it's slightly different. So when you have cross product and you think of it as sweeping, is what in physics we call the right hand rule or something, right? Okay, so some people in physics use the right hand rule like this. I don't like it. Okay, if you think of cross products as sweeping, okay, cross products as sweeping. So let's say R to B. Okay, this is my right hand, just in case it's flipped or something. Okay, so let's say my index finger is vector A, so vector A, and vector B is my thumb. Okay, so if I am going to do a cross product, I'm going to sweep, let's say vector A cross B, so vector A sweep to B. Okay, so let's leave the vectors here. I'm going to use my right hand, this is my right hand. Yeah, I'm going to use my right hand like this. My fingers are going to sweep from from vector A to B, like this. And my thumb will point in a very specific direction. You can't point your thumb elsewhere when you sweep like this. Okay, you sweep like this. So this thumb, the direction is the direction of the cross product. And the cross product gives us a vector. The thumb, when you do this sweep, your thumb points in the direction of A cross B, or sorry, R cross B in this case. Okay. Now, another thing to take note, okay, is that when you sweep across, you think of it as when you sweep across, okay, the more you sweep, so like for example, the vectors are like this, then there's maximum sweeping. The vectors are like this, then there's sweep a little bit, right? There's nothing much to sweep. Okay. So when you sweep a lot, this thumb, this vector that grows, sorry, this sweep will grow this vector. The more you sweep, the more this extra, this normal vector grows. So for example, let's say when I do R cross B like this, the vector grows out. It grows into the page, sorry. It goes into the page. So it points into the page. Okay, so the vector is growing into the paper, into the screen. Okay, but if I do B cross R, okay, the other way. So let's say I do B cross R, maybe I draw like this. I sweep the other way instead, right? So I sweep the green color way. Then my vector will grow in this other direction, out of page. Okay, so this is out. Let me just write down because it looks a little bit difficult to see. It's in. Okay, this is how to visualize. It's not exactly important in H2 math to know the direction. Okay, so the direction doesn't really help us, but it's just to visualize, okay, and gain some intuition. Okay, So you don't need to know how the sweeping direction matters. What you need to know is that the more you sweep, the more these black or green color vectors will grow. For example, if instead I sweep, let me erase this a little bit. Okay, if instead I have a vector B like this, okay, and I sweep to a vector R that is, let's say, like that. Okay. Let's say I have a vector B sweep to a vector R like that. Okay. Instead of doing that, let's do something less confusing. Let's say a vector that is like this. Okay. To make things clearer, let me draw this diagram a little bit less. Let me draw the angle a bit smaller. So let's say the vectors are like this. Okay, so I have this sweeping. Okay, then again, the green color arrow points the other way. Okay, so in this case, in this first case, I have decreased the angle between them, which is why the arrow over here that is created by this sweeping is very short. But now in this case, let's say I'm going to sweep the vector R cross B. So from R to B, there's a lot of sweeping because it's a very big angle, right? It's a very big angle. So when I do a lot of sweeping like this, the vector grows a lot. Okay. So think of it as when I'm sweeping, right? When I'm sweeping, the thumb grows. Weird, but yeah. Okay. So let's say the vectors are very, the angle between the vector is very small. Then there's very little sweeping. So the vector, the cross product vector grows out. I don't think you can see it. But a cross product vector grows out very little. Okay. But if the vectors are pointing very different, like let's say perpendicular, right? Then there's a lot of sweeping. Okay. Then the vector, the normal vector that grows because of this sweeping will be very big. For example, like this. Hopefully you can see. Okay. So in picture, it looks like a longer arrow going into the page like this. Okay. So the idea is that more sweeping, okay, more sweep means bigger normal vector. Okay, or longer, let's call it longer. Longer normal vector. Okay, this is the visual intuition that you should have for cross products. Okay, now if you sweep the other way, same thing. So let's say I sweep the opposite way again. So instead of the black color way, I'm going to sweep the green color way from vector B, okay, to vector R. Then I will grow my vector the same length because it's the same amount of sweeping, but in the opposite direction. The vector grows out of page. There you can't see the R. Am I? Okay, like this. So the vector grows out of page. Okay, this looks very, very ugly, but I'm trying to draw like 3D. I'm trying to draw like the arrow pointing out of the page as best I can. Okay, so I'm just gonna label that this is out of page. Okay, so I draw like bigger than this one to show that is more out of page. Okay, so let me just draw a smaller. Okay, I'm horrible at this. Okay, so hopefully the picture looks a little bit useful at least. Okay, so the main idea, the main takeaway from here is that when there's more sweeping, okay, the angle is bigger, there's more sweeping, your normal vector grows out more. It's a longer normal vector being formed. Okay. When there's less sweeping, like in this first case, let's write down less sweep. Okay. Then you get a shorter normal vector. Okay, shorter normal vector. Okay, so this intuition will help us quite a bit later on. Not as much as the other way, but good enough. Okay, this sweeping idea, okay, the sweeping idea will help us think about or help us understand visually the magnitude of the vector that is formed when you do a cross product. Okay, less sweeping, smaller vector, because the more you sweep, just think, okay, I don't know how to do this animation, but if I could, okay, I will show that, for example, if I sweep the vector, then it's like the color is being highlighted, right? So the color grows when it sweeps across, okay? When it sweeps across, then the vector grows longer as it comes out, so that when there's more sweeping, when there's more sweeping, then the vector will grow out. Okay? So when there's less sweeping, then there's less time for the vector to grow, so the vector is shorter. Okay? This is the best I can do with just drawing on my iPad. But hopefully one day I can do the animation to show what I really mean. Okay? Okay, now let's go on to the other way to think about cross products. Okay? The other way to think about cross products is very simple. It's using this same picture. Okay. When you squash a mosquito using your dot product, using your projection, the mosquito gets collected on your palm like this squashed part, right? Okay. Now, back to the slightly gross, mosquito example, right? So the other thing I think about is that when you squash a mosquito, the mosquito dies. That's one thing. The other part of the mosquito that goes missing, right? Because you see the mosquito was this long and now it's this long. So some part of the mosquito disappeared. So I think about it as the mosquito's soul leaving the body. The body is collected on my palm. Something disappears when it dies. Okay. So this something that disappears is this phantom vector. Okay. This vector, okay, we will show later using some using math, right? That this vector has the same length as this vector, the vector that grows out. Okay, we will show using working later. We won't don't try to visualize why it's the same. I don't think there's a good reason for that. Okay, just imagine that the part of the mosquito that gets destroyed left its body as a soul or something, right? So this is the missing part, is the soul that left the mosquito's body, okay? And this is the same length as the cross product, okay? So for example, in this case, this would be, okay, in this case, this will be vector M cross vector D hats. Sorry, vector M, not hat. Vector M cross vector D hat. But again, I'm not talking about a vector here because cross product gives us a vector. I'm talking about the length of this vector. So this is the modulus of M cross D hat. Okay, this should be how you link between your dot product and your cross product. And that's somewhat the reason why your cross product and dot product have pretty similar formulas. Okay, I don't like to call them formulas, lah, but yeah, it's pretty similar formulas, right? You see modulus, modulus, and then cosine or cosine or sine. It's just that cross product, you have a vector at the end, n hat. The n hat is because you are growing a vector that is normal or perpendicular to both of your red and blue vectors. Okay, so it's perpendicular. Either it grows out of the page or into the page. And the length is this ghost here. This is soul here. Okay, the mosquito ghost. Okay, so this is the link between your two different types of vector dot and cross product. Okay, let's move on. Let me just use another page to summarize this. Okay, I'll just use this page. So this page tells us about dot product and cross product. Okay, so you can read through a little bit of it. All the words here is a shorter version of what I was trying to illustrate just now. It's just that if you read through, it's a little bit, well, one thing is that it's a lot less naggy, but the words don't really help you visualize. So I'm trying to help us visualize the ideas just now. Okay, but in summary, our dot product is this. Okay, but remember just now when I tried to, in a sense, derive it using the analogy, it's not a real derivation, but I derived it using the analogy. Our dot product is written like A dot B hat equals to modulus of A cosine theta, where theta is the acute angle between, acute or obtuse angle between A and B. Okay. So why is it slightly different? Simply because when I write my B hats, what I'm really doing is, this is just B, vector B, divided by modulus of vector B. And what I can do is I can multiply this modulus of vector B over to the right-hand side. So this will return us our dot product, so-called formula. Okay. They are equivalent. You don't have to, there's no such thing as the correct formula or the wrong formula. These are both perfectly fine. It's just that the first one, which is what I talked about, is better to think, is more intuitive, and it makes a little bit more sense because A dot B hat gives us something that we can get from just a right angle triangle and simple secondary school trigonometry. This one is a formula that usually people memorize. It's not very helpful in terms of understanding. Okay, so I will use these two interchangeably. Just know that my derivation or my way of explaining this is using the first way, but the second way is just is obtained by just by multiplying the modulus over. Okay, so this is the dot product. Okay, now vector product is a little bit different. Cross product is a little bit different. The only thing, okay, one thing that you notice is the sign is instead of cosine is sine, right? So cosine for the dot product, sine for the cross product. Okay. The other thing is that I have n hat over here. This is not dot lah. This dot is just multiply. Okay. So this whole thing is a number. This is the direction. Okay. So remember again, a vector has two pieces of information. We have the magnitude of the vector. Okay. And then we have the direction of the vector. Okay, but actually, I have to warn a little bit. Yes, this is somewhat the magnitude, but we shouldn't think of it this way. Okay, I'm so sorry, but we shouldn't think of this very literally like this. Magnitude, yes, is related to the magnitude, but it could be positive or negative because sine theta is, okay, sine theta is always positive. Sorry, wait, hold on. Yes, it's always positive. Oh, then nothing is wrong. Sorry, nothing is wrong. Okay. Yeah, nothing is wrong. Sorry. This is perfectly fine. This is perfectly fine. I'm going to erase this. Okay. Magnitude of the vector that you grow when you sweep from A to B. Okay, so remember, we are sweeping from vector A to vector B. A cross B. We sweep from vector A to vector B. When we sweep across, we grow a vector that is perpendicular to A and B. Okay, perpendicular, this tells us that, sorry, the perpendicular part is written here as n hat. N hat is the normal vector, a vector that is normal to both A and B. And then the length of that vector that grows out has this magnitude. Okay. Now, if we want to take out the magnitude, instead of just writing vector, sorry, modulus A, modulus B, and sine theta, sometimes we just write modulus of A cross B. Okay, modulus of A cross B is modulus of, sub in the whole thing, modulus of A, modulus of B, sine theta, and hat. Okay, this is, okay, let me move down so that we can see more clearly. This is modulus of A. It's like, it's already modulus, right? You modulus again, is still the same thing. So modulus of A times modulus of B, which is still the same, times modulus of sine theta times modulus of n hat. Okay. Modulus of n hat is the magnitude of unit vector. Okay, so the magnitude of a unit vector is 1, which means we can just ignore that, right? Modulus of sine theta, the good thing is that for theta, sorry, for sine, when theta is acute or obtuse, sine is always positive. Okay, so because sine is always positive, when you take modulus, it's still the same thing. So it's the same thing. It's this magnitude. Okay, it's just that it's a bit easier to just put the magnitude here rather than just, you know, write this down, because it doesn't really make much sense. Okay, so this is dot product and cross product. Let's see how we can use them. Okay, so first thing is, sorry, let me skip this part first. Let's go on to this. Area of parallelogram and area of triangle. Okay, if I scroll back up to recall this picture over here, right? This picture over here. Let me just, okay, let me just bring this over to those pages there. Okay. Okay, I'll put it here. So I want you to think of this when you look at your area of parallelogram and area of triangle. So your area of parallelogram, as it turns out, is the same, okay, as the magnitude of this normal vector that grows out when you sweep your vectors. So when you do, for example, B cross R, B or R cross B, or whichever way, doesn't matter, right? You get a vector that grows out, either the green color side or the black color side. This vector, if you measure the length, the magnitude turns out to be the same as the area of the parallelogram here. So when you sweep across, okay, so think of it like this. When you sweep, for example, OA to OC, okay, like this, when you sweep across, what grows out is this. Okay, try to imagine the animation. Unfortunately, I don't know how to do animations like this, but when you sweep across, so let's say from A to B, right? So let's slowly sweep. If I sweep a little bit from red to here, right? So if I sweep this little part, what I'll create is this very skinny parallelogram. Okay. Now when I sweep a little bit more, so when I sweep a little bit more, okay, so when I sweep a little bit more, so I've swept this angle, what I get is this parallelogram. Okay, like this. Okay, so parallelogram. So the more I sweep, the more this parallelogram opens up, right? The more I sweep, when I sweep until, let's say, this part, when I sweep until here, the parallelogram opens up like this, kind of like unfolding a table, if you want to think of it that way, right? If you can try to visualize, when I sweep across, so, okay, I'm going to sweep from here to here, like this, okay? So when I sweep across, I have a parallelogram opening up, like this, okay? Yeah, so if you know anyone who can do animation, I don't mind paying someone to animate this for me. This is going to be very, very useful for visualization. Okay, unfortunately, this is the best I can do now. So opening up a parallelogram like this, like unfolding a parallelogram. So the more you sweep, the bigger the area of the parallelogram. At the same time, the more this normal vector grows out. Okay. The good thing is that they are all equal. You just don't think too much about like, yeah, don't think about like, if you do, the length of this vector, right? It's like how many cm? Let's say it's like 5 cm. Then the area is like, let's say 5 cm squared. It's not the same dimensions. Okay, ignore that. Okay. Yeah, please don't think too much. Okay. But the number, the 5, is the same. Okay, it's very interesting. Yeah, okay. The area of the parallelogram that gets opened up is the same as the length of the vector that grows out. Okay. So area of parallelogram is simply the modulus of A cross C in this case, right? The modulus of the cross product gives you the area of parallelogram. Okay. Think of when OA sweeps to OC, a parallelogram opens up. Okay. Then more sweeping, again, more area. Okay, more sweep becomes more area, and the same sweeping motion will, the same sweeping motion can be thought of as a way to grow this normal vector. So longer normal vector. Okay, so more sweeping, a longer normal vector grows out, and also a bigger area for your parallelogram opens up. These two have the same magnitude. Okay, so area of parallelogram can be obtained by doing a cross product. Area of triangle is simply cutting the parallelogram in half. So half the modulus of cross product. Simple. Okay. Okay, now let's go back to collinearity. Okay, let's do this quickly. Collinearity. Okay, let's look at the word. Co means like a relationship between two things or more than one thing, right? Co, like colleagues, right? Collinear just means between us, we lie on the same line, okay? Collinearity is just a relationship that says a bunch of points lie in the same line or on the same line. Okay, they lie in one straight line. Okay, to show that a bunch of points are collinear, you just form a bunch of vectors and you show that the vectors are parallel. Okay, so let's check. For example, let's just do very quickly. Check if the following points are collinear. Okay, so first of all, okay, question 1. If I want to check if these 3 points are collinear, what I have to do is I have to form 2 vectors. For example, let's say I form vector AB and I form vector AC. Okay, vector AB, let me just write it out because I'm quite slow. Vector AB is vector AO plus vector OB. Okay, vector AO is vector OA but negative, and then plus vector OB. So this is vector OA but negative everything. So like this, plus OB. So let me just copy down OB. Okay, so this is 1, 0, 2. Same idea. AC, okay, I can do the same thing. Okay, and then I'll get minus 1, 0, minus 2, plus 3, 0, 6. Okay, and this will be 2, 0, 4. Turns out that these two are related by, or they are different by just one scalar multiple, right? So we write down, since AB or vector AB is equals to half vector AC, right? So if you want to write it even more clearly, you can write out, you can factorize out the 2 and say that it is 2 times 102, which is 2 times AB, like this also can. Okay, but because you say that these two vectors are just different by a scalar multiple, therefore vector AB is parallel to vector AC. Okay, and points A, B, and C are collinear. Okay, so I'll skip the second one. It's the same thing. It's just I don't think they are collinear. Okay. Okay, you know what? I'll write down the answer. Okay, for question 2, you just do some workings and you say, since vector AB is not equals to K times vector AD in that case. Okay. For all K in R. So no matter what real number you multiply to vector AD, you can never get a vector AB. Therefore, vector AB is not parallel to vector AD. Not parallel, you can write like this, but it's better to just say, and they're not parallel. Not parallel. Okay, so A, B, and D are not collinear. Okay, so collinearity is not too difficult. Just make sure you know how to just recap a little bit and then should be fine. Okay, the whole idea is that they lie on the same line, which means if they lie on the same line, for example, point A, point B, and let's say point C, and then maybe point D is over here. Okay, so what you can do is vector AB and vector AC must be parallel. But if you compare, sorry, if you compare vector AB and vector vector AD like this, they are not parallel, right? Because vector AB and vector AD are not parallel, they cannot lie on the same line. And also because vector AB and vector AC are parallel, points A, B, and C lie on the same line. Okay, so that's collinearity. The last thing for this first chapter that we are going quite slowly for is ratio theorem. Ratio theorem is going to be very useful, okay, for foot of perpendicular. Okay, sorry, not for a perpendicular. Point of reflection. Okay, foot of perpendicular is needed for point of reflection. So, you need to find foot of perpendicular, then apply ratio theorem for this. But let's talk about ratio theorem first. Ratio theorem, I don't recommend trying to understand it. Okay, just remember how it looks like. Ratio theorem, draw out this picture. Okay, so let's draw it out. The nice diagram is here, but let's draw it out on our own. Let's say I have a vector A and I have a vector B. Okay, and remember, vectors are instructions, and instructions can be like recycled. They can be copy pasted somewhere else. So maybe vector B is like, let's say a vector that describes from this point here to this point. Vector A is from this point to this point. But I can just move my vector B, which is just a set of instructions to describe here. So I can move my vector B, right? It's not tethered to any points. I can move my vectors around. So if I draw my vectors A and B like this, I can join the tips of the arrow. And I can say that, for example, let's say I cut this dotted line into two parts. I cut it here. Okay, I cut it here. Okay, sorry. I cut it here. Let's call this point maybe point C. Okay, so let's call this point A. Let's call this point B. And let's call this here point O, origin. Okay. To get to point C, if I know these two lines, or at least if I know the ratio of these two lines, I can find the vector OC. So I'm going to do it like this. I'm going to highlight this with red color. I'm going to highlight this with blue color. Okay. Let's call this maybe, let's use different symbols from the above one. Okay. Let's just say this is, let's say this is lambda. Okay, lambda. And this is 1 minus lambda. Okay, this used to confuse me a little bit when I was a student, but when you call things like this, lambda and 1 minus lambda, what they mean is just this whole thing add together, 1 minus lambda plus lambda, that's just one whole. That means lambda is a fraction. It's just like, lambda is like maybe 2/3. So red color part is 2/3 of this whole dotted line. Okay, whatever it is, it doesn't matter. There's no need to understand it. Just draw out this picture. And then in order to find my vector OC, so vector OC is equals to cross. I'm going to jump across. So I'm going to use a different color. Sorry. Okay. I'm going to use a different color, green color. I'm going to join the red color and the red color like this. So let me multiply those two. I have lambda times vector A. I'm going to jump across to the blue color times blue color. Okay, so I have 1 minus lambda times vector B. Okay, if I add those up and I divide by those two, okay, those two proportion, or the ratio stuff, right? If I add up those two, this is how you use ratio theorem. Okay, so remember it visually. Don't remember this equation. This is not a formula, not an equation. Just remember the picture, okay, that when you have two arrows, right? Two arrows joined at this little dot here, okay? It can even be like this. So let me just draw a different picture. Let's say your arrow points like this, and then your other arrow points like this. That still works, because if you have two arrows joined together, you connect the heads of the arrow with a dotted line. and you divide this into two parts. Let's say now I divide it here. Okay. To find this arrow, let's call this a vector C. This vector C is simply, okay, it's a simply this blue color times the blue color vector, and then this red color part times the red color vector. Now let's say I use this as lambda, this is mu or something, right? So then this will be lambda times vector B plus mu times vector A. Add up those two numbers. Okay, so this is ratio theorem. Remember the picture. Please don't remember the formula itself. Okay, ratio theorem usually is only going to be used for point of reflection. Sometimes you get some weird questions, then maybe you need to use ratio theorem somehow, right? But in the usual cases, you only use ratio theorem for point of reflection. Okay, we are now finally done with the first chapter. Okay, so I think I mentioned this before, but in the three vectors topics, okay, so let's call it vectors, lines, and planes. Vectors should be the bulk of your revision. Your revision should be just do a brain dump on how to visualize and how to think of all these vectors. How do you add vectors? How do you multiply vectors, whether it's dot product or cross product? Okay, how do you use vectors to create things? Let's say I do a dot product, what do I get? I get a projection. Let's say I do a cross product, what do I get? I get a few things. I get a parallelogram. I also get a normal vector. How are they related? They have the same magnitude. Okay. And then the last thing is something that's a little bit odd. This is just ratio theorem. Perhaps I should have shifted this up to the addition of vectors part lah. But yeah, ratio theorem is just quite standalone. So I just wanted to point out that it's useful for a point of reflection. Now let's dive into lines and planes. Okay, lines and planes. I hope I didn't miss out anything, but let's just skim through this first. So for lines, I included a scope here. For planes, I forgot to include this box. So I will type it out later, then I will send a revised version of this box. I'll include it for planes. But basically, I want to type out a scope like this. This can be used as a checklist for your revision. Okay, so these are all the things you need to know for lines and then for planes, just that I haven't typed it out. Okay, so these are all the possible concepts that can be tested. Okay, it's pretty exhaustive. It looks quite short here because for the planes, okay, I'll just show you. Every one of these bullet points is like one section. Okay, so like parametric form, Cartesian form. Okay, 1, 2, 3, yeah, a lot of them. Okay, so if I scroll all the way down to the planes part, okay, I forgot to include the table, but it's essentially all of these headers here, all the sections and subsections. So there's a lot more for planes lah. So the scrolling is, yeah, quite long. Okay, I included some extra stuff at the end. So this is for three planes. We rarely see three planes nowadays for our H2 math papers. But nevertheless, I will just include this here, but I won't talk much about it. Okay, so this is just, I'll show some pictures, but not really do the math behind it. Everything else, I don't think I can do everything and calculate all the numbers. So what I'll do is I will give you a kind of like a recipe to solve each of these problems, but I won't calculate everything out lah. Okay. Okay, so for lines, first things first, for lines and planes, I also want to build visual intuition. Okay, let's discuss lines first, because lines are familiar to us from secondary school. We know y equals mx plus c. So let me just drop it down. y equals to mx plus c. Okay, what is there to learn from here? This is not for fun. It's not just to compare. Okay, y equals mx plus c is a pretty similar form to our to our line equation. Okay, position vector r, arbitrary position vector r equals to some vector a, some position vector a plus lambda times some direction vector. Okay, of course we write down our lambda in r, but yeah, that's not very important here. In this case, I'm going to compare this with y equals mx plus c, so that we understand this very well. Okay, let me shift this around. So okay, mx plus c is more familiar to us, so I won't touch this new one, right? This is relatively new to us. I'm going to shift mx plus c. What I'm going to do is I'm just going to swap these two around. Okay, what's more is I'm going to swap these two around as well. I'm going to put x in front, put the m behind. Okay, so this will look a little bit weird, but now we have a one-to-one matching. Okay, so I will explain how these are similar. Okay, like this. Okay, I should probably use different, I'll just use different colors. Okay, so that I can talk about different things slightly differently. Okay, what color? Okay, whatever lah. Okay, anyhow color. Okay, all right. Now let's try to talk about y equals mx plus c first, just written in a weird way. How do we describe a line? Okay, we need two pieces of information to describe a line. Y equals mx plus c is in 2D, so it's a little bit easier to capture this information. We only need two things. We need our gradient, which tells us, in a sense, the direction of the line. Okay, so this tells us the direction of the line, right? The orientation of the line. Okay, so orientation of the line. The other piece of information is where the line is. For example, if I draw a line, like this, this line could be in the middle of my screen, could be at the top of my screen. Oops, sorry. Could be the bottom of my screen, left side, right side, whatever side, right? So we need to discuss, we need to write down, we need to talk about the position of the line, where the line is. Okay, so what tells us the position of the line? That's this stuff. Okay, so we have two pieces of information that will describe a line. First thing is the direction or the orientation, the gradient. Okay, we won't call it gradient here because it's not helpful for 3D case. Okay, we'll just call it direction or orientation. The second thing is a position, where the line is. A line can be pointing, let's say, north and south, but you can have something that's pointed north and south anywhere in the world, right? So we need a position, somewhere to put the line. Okay, these two pieces of information fully describe a line. So what are these other two things? How come there are two other pieces of information, right? Okay, so really a line is described by two pieces of information. These two things are not information about the line. Okay, these two are just coordinates. It's just like your y and x are your coordinates. In this case, this is not really coordinates, but they are still quite similar. Okay, in a 2D line, right, y equals mx plus c, x is the independent variable, right? This is our independent variable. independent variable. Okay. Y is our dependent variable. Okay. Why I bring this up is because how do we think of independent and dependent variable? We choose to change our independent variable to see what happens to our dependent variable, right? Independent means it doesn't depend on something else, right? We get to choose or we get to vary it, right? Dependent is because whatever independent variable we put in, whatever value our independent variable takes, the dependent variable depends on certain factors like M, the gradient, or C, the y-intercept. Okay, so those two numbers that describe the line, together with our input, the independent variable, we get a dependent variable. Okay, and those two form our coordinates, okay, of points on the line. In the 3D case, in the vectors case, it's going to be slightly different. Our independent variable is not one of the coordinates. Our independent variable is a third party, or I guess fourth party, because in this case we have our position has 3 coordinates, 3D. So this is like a fourth party, right? We call this a parameter. This parameter is something like our independent variable. We get to choose the parameter, or rather, any choice of a parameter gives us a certain point on the line. The parameter is something we choose, just like the independent variable. We choose what to sub in, we see what we get. Same thing, we choose what to sub in, we get a certain point on the line. Okay, so this R is an arbitrary position vector. Okay, or position vector of an arbitrary point. Okay, so this should help us understand a little bit better the vector form of a line equation. Okay, this is still not too difficult, but I want to point out something that is very, very important in recent years. So in recent years, A-level questions, or at least H2 math, okay, so H2 math questions tend to start becoming a bit more conceptual, right? So in our whole education from primary school until JC, usually in math, we are only expected to evaluate certain things, to compute certain answers. Things like calculus, they ask you to differentiate. You just need to know how to differentiate, how to sub in some numbers and get an answer. But in recent years, O-level, A-level, unfortunately or fortunately, we are seeing a lot more questions on conceptual understanding. So let's talk about some conceptual understanding about this line equation in vectors. Okay. So if I ask you, what is the interpretation? Usually they'll call it geometrical interpretation. Okay. So what is the interpretation of this equation? In the question, they don't call you a line. So I'm not going to tell you it's a line first. I just show you vector R equals to vector A plus lambda times vector D. What does this describe? Okay. This equation, to be very precise, okay, is not a line. This equation talks about points. Okay, points that are collinear. This is not about the line. This is about the points. Okay, so we need to be very, very precise here, because it's okay if you don't trust me on this, because this is pretty new to like if you look in your 10-year series, you will see, I think one of the papers in recent years, they tested something like this on conceptual understanding. Okay, the questions look exactly like the ones in this yellow box. I think they tested just the simple one, but just in case, I also included some extra ones. Okay, so if you don't believe me, it's fine. Okay, go and take out your TYS, look at the past year papers, you should see something like this. Same for plane equation. And I can't remember something else. Okay, so 3 parts. So one part is line equation. The answer, hopefully the TYS answer is the correct one. The correct answer, you shouldn't mention that this is a line equation first. You need to focus on the points. This equation tells you about points. Okay. Just to also share a little bit, y equals mx plus c is not about the line as well. It's talking about this, the dependent variable. How the dependent variable is related to the independent variable. Somewhat like what you will see in the linear regression and correlation topic. Okay, so that might help you a little bit with understanding that, but let's come back to vectors. So the important part of this equation is really the points described by this vector R, this arbitrary position vector. Okay, so if I ask you what the interpretation or geometrical interpretation is of this equation, okay, the first thing you should say is not a line first. You shouldn't say that it's a line. Okay, you shouldn't say it's a line. Okay, you should say that this describes, okay, this, okay, it describes the set of set of points that lie on a line that passes through, okay, it's quite long, but this is the perfect answer, I would say. Okay, so it describes the set of points that lie on a line. Sorry, it's not even a set of points. It describes the, okay, it describes the position vector, the position vectors of points that lie on a line passing through, or that passes through the point with position vector A, okay, and is parallel to vector B. Okay, vector B. Okay, so this is like the perfect answer lah. Okay, I'm a little bit harsh or a little bit strict when it comes to this kind of precise definitions, but if you want, you can still call it a line. It's just that you cannot just call it a line. You must tell me that it's talking about all the points on this line, which sounds a little bit silly, but you need to mention the points, not just the line. The line is just the relationship between those points. You are really talking about the points that just so happens to line up in one line. Okay, that's a nuance behind it. So the main focus should be on the points. In fact, it should be the position vectors of the points, because these things, these objects here, like vector R, is a vector. It's not a point. It's the position vector of an arbitrary point. Okay, so it describes the position vectors of points that lie on a line. Okay, so it's the position vectors of points that lie on a line, blah 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 blah. Okay, that's one whole phrase. So this whole sentence should be read like this. This is me being very nitpicky, very trying to be very precise. Okay. But this is good. Okay. A less strict answer would just be, it describes the line that contains the point with position vector A and parallel to vector B. That's the bare minimum. If you want to talk about the line, then you should say like that. The line that contains, the line, okay, so I really cannot. And you need to talk about the points, okay? You need to talk about position vectors of points. So try to remember this way of describing things, okay? So the language that you use in your head is also very important when we talk about vectors. Unfortunately, we pay too much attention to the things like formulas or things how to find answers rather than conceptual understanding. So I'm being very strict here about language, about the objects in equations that we see in vectors. Okay, if you look at this equation, there are no points. Okay, in fact, there are no coordinates. It's just vectors. We are talking about position vectors. We are talking about this point, but we are really focusing on the position vector. We're also talking about this direction vector. It's all vectors, not points. The lines or the points are just like byproducts of this equation. Okay. 2 and 3, I'll leave it alone. So you can think about it because the template is the same. It's just you know, instead of A and instead of B, you have something else, right? Like all these things, literally the same word for word. Okay. Now let's talk about the equations. Okay, let's talk about the equations. So I introduced lines using vectors, okay, with this form of the equation. I can write it in two other ways. So this way that I just written down is called the vector form. Okay, it's called a vector form because we see a bunch of vectors. That's about it. Okay. The other two forms can easily be obtained from this equation. Okay, so the other two forms are called parametric form and Cartesian form. So I wrote down over here, parametric form is obtained by splitting the vector form into its respective components. We get a bunch of parametric equations. So recall like things like your differentiation, right? Differentiation, you have parametric equations, parametric differentiation, right? So you have a bunch of parametric equations. In this case, is x in terms of lambda equals to 1 plus 4 lambda. Y in terms of lambda, this is 2 plus 5 lambda. We have z as a function of lambda, which is 3 plus 6 lambda. Okay, parametric equations. And as I've mentioned, lambda is a parameter. It's like the input, a third party, or in this case, I guess fourth party variable that we use to kind of like slide along the line to choose which point we are talking about. Okay. Now, before we go back to the intuition part, I'm still not done, I'm sorry. Next thing is Cartesian form. Cartesian form, I'll just put it out there. Cartesian form is very useless. Okay, it's just easier to write out. Okay, you can write out like, you can multiply by 4, 5, and 6 and whatever. You can write it out in a nice one line in your foolscap, rather than things like, you know, spanning 3 lines or vectors with like brackets that are in columns, right? So it's a bit easier for like examiners or like teachers to type it out in Cartesian form. It's easier to type out, but it's useless in calculations and solving problems. Okay, so Cartesian form, you only turn the line equation into a Cartesian form when they ask for it. Otherwise, it's useless. Okay. So what we really need to know is, of course, we need to know how to turn it into this. In this case, it's just from your parametric equations, make lambda the subject. Okay. Okay, so make lambda the subject. Okay, and equate all of them. This is how you get the Cartesian form. And usually it's only worth like 1 mark, unless they're exceptionally generous. Usually it's only worth 1 mark. The more important thing is to know how to switch back, which is still very simple. You just let each one be equals to lambda. Okay, so let me just do it like for this example. So to change from Cartesian to vector form, okay, what we need to do is we need to use the parametric form. Okay, we see a lot of parallels between vectors and complex numbers. I just want to point out here, it's quite similar to how in complex numbers, right, we see things like, let's say, Cartesian form, same thing, Cartesian form. Then we use our trigo form to turn it into the exponential form. Okay, so it's quite similar. It's quite similar. It's only the only difference is that for complex numbers, these two are useful. The trigo one is somewhat useful. It's for proving. But in vectors case, Cartesian form is pretty much useless. So don't ever use it unless you're asked to do it. Okay. So let's say they give you Cartesian form. We want to change it back to the more useful vector form. In fact, it's the only useful one here. So parametric form is only useful if you want to key it into your GC for simultaneous equation. So let me just sheet on this one. I'm just gonna say that this is useless. Okay, this is useless, really useless. Parametric form only useful for simultaneous equations. So if you want to solve simultaneous equations using your GC, then of course you need to split it into the parametric form. Then you can key in 1, 2, 3 simultaneous equations. For Cartesian form, useless. Okay, so let's learn how to change from Cartesian form into the more useful vector form. Okay, so from Cartesian form, let's use this example. X minus 1 over 4, y minus 2 over 5, z minus 3 over 6. Okay, the first step is we write it as each one is equals to lambda. So we write a system of linear equations. Usually what I'll do is I'll put a left bracket, but I won't put a right bracket. So this tells us that this exists, the bunch of equations I'm going to write down exists as together as a system. Okay, so the first one is lambda equals to this. Second one is lambda equals to the second one. Third one is lambda equals to the third one. Okay, then I'm going to make x, y, z the subject. Okay, so I'm going to do equation by equation. First one is going to be 4 times lambda, then I plus 1. I get this. Okay, just do it slowly, it's okay. I'm just writing out the answer. Then this one, next one will be like this. Okay, the last one will be like this. Okay, so this is the parametric form. Okay, so first step is to make lambda the subject, then write in parametric form. Then from here, you write it as your vector form. Okay, so okay, to arrange it better, because it's a bit squeezy, let me just put it like this. Okay, so make lambda the subject. Okay, make x, y, z the subjects. And the last one, the last step is to just convert into vector form. So vector form. Okay, so what this looks like is just vector r or xyz is equals to vectors vector, and then I collect the 1, 2, 3 plus take out the lambda and then 4, 5, 6. And then of course I need to write down lambda in R. Okay, so I just take out like this, like this, like this. Okay, so these are the 3 steps. Okay, so this is quite important. Let me go back to here. I'll just very quickly mention that how the way to think of your vector form of the line equation, right, is that it tells us how to get to the line. Okay, so see this line, I meant for it to be gray. It's just very slightly, like pretty dark gray. Okay, but anyway, this gray color line, okay, I want to get to the line. How do I get there? I follow OA, okay, which is this vector here. This is the position vector of a point on the line. This allows us to get to the line. Okay, this is the first step, to get to the line. The second step is to, let me shift it up so I can arrange things better. Okay, so first step is to get to the line. The second step is to, this is the direction of the line. Okay, okay, this is the direction of the line. So think of it as this is the direction to look. Okay, so see, we walk from the reference point, which is like our home, we walk to the line, and then now we need to look in the direction of the line. So I look, for example, there. I look in that direction. Okay, so I look in that direction. Okay, I look in that direction. Okay, so I look in that direction, but I haven't walked yet. I'm still here. I'm still here. Okay, now how do I walk along the line? I walk along the line by varying. Okay, so vary lambda to walk along the line. Okay, so when I vary lambda, for example, lambda is like the number of steps. So I look in that direction, and if lambda is 1, I take 1 step in that direction. If lambda is half, I take half a step in that direction. If lambda is negative, then I take like let's say -1, then I take 1 step backwards. Okay, so for all choices of lambda, if I collect all those choices of lambda, so lambda can be any real number, all of those gives us a set of all position vectors of all the points on the line. Okay, so again, the subject of this equation, okay, so we make things a subject, right? We make something the subject, means put that thing on the left-hand side and nothing else on the left-hand side. So the subject of this equation is the position vector. That's the main, the star of the show. It's the most important thing, okay? Not the line itself. Okay, so this is how to think of the line. Okay, before we go to planes, let me just run through all the possible concepts to be tested for lines. Okay, and I'll briefly talk about how to solve each of these things. Okay, okay, I will try to go a bit faster from here because these are just examples using the things that I talked about previously. Okay, so the first thing, we talk about lines. We talk about how to interpret the line equation, right? Now, how do I form the equation of a line? I can form them from a few, if we are given a few pieces of information. For example, if I am given one point that lies on the line, okay, let's say a teacher is interested in a certain line. They tell us, okay, I throw you a piece of information. I have this point on the line. I know the line is along this direction. What could the line be? Okay, so that's a question, right? It's a very simple question in this case because you already have the two things you need for the line, right? Right before this, I talk about how to visit the line. I need to first walk to the point. The point is here, point A. Then I need to look in a certain direction. Good thing is they tell us the line is parallel to this vector. Okay, so I need to look in this direction. Okay, so I write down, I need to walk to that point. How do I walk to that point? I need the position vector of that point to walk to that point. Okay, then I need to look in the direction of that vector. Let me add that vector. Okay, sorry, let me not add it yet. Okay, let's just look in the direction. Okay, let's just write it down. This is the direction of in which I should look. Okay, so I look in this direction. Now I want to visit the points on this line. How do I do that? I'm already on the line. Okay, good thing. I'm already on the line. Now I just need to choose how many steps to walk in this direction I'm looking in. I can walk 1, 2, 3. Any fraction, any decimal, any whatever number, right? Any negative number. In fact, any real number of steps. Okay, or real number of distances, okay, in a sense. I think of it as steps because it's easier to think of it that way. So I can scale this by any lambda. Lambda can be any real number. Okay, so this will give us all of the possible instructions on how to walk to any of these points on the line. Okay, I can't stress this enough. The subject of the equation is the position vector, not the line, not even the points. It's the position vectors of those points. This is the line equation. Okay, we call it the line equation because it tells us something about the line, but it's not talking about the line. It's just the line is a byproduct. The line is just so happens that these things we're talking about lines up in the line. Okay, something like that. Okay, next one. So example 1 done. Next one, if we are given 2 points on the line, okay, I'll go a little bit faster now. If we have 2 points on the line, draw a line first, put down 2 points, label them. Okay, vectors is a very, very visual subject, very visual topic. So I always recommend you to draw pictures. Vectors, I would say, is the most visual, other than maybe graphing techniques, because literally you draw graphs. Vectors is the other topic that is very, very visual. So please draw pictures. You don't have to draw it nicely, just draw enough for you to understand. Okay, so a line, and this line is called L. Okay, it has these 2 points. So how do I get to any point on this line, right? Because again, the subject of the line equation is the position vector of an arbitrary point on the line. So a vector is an instruction. I want to find out all possible instructions for all possible points on the line. Okay, I need to first tell someone to walk onto the line. So for example, there's someone is at the origin O. Okay, there's a different color. Origin O. Okay, I need to tell them how to visit the line, maybe to point A or point B, whatever. Okay. Yes. Okay, from O to A, right? So in order to walk from origin to A, okay, I need to tell them that I need them to walk from O to A following this vector OA. Okay. Now that they are on the line, I need to tell them to look towards the direction of vector AB. That's the direction vector of the line, vector AB. Okay. Then when I tell them to loop there, I can say that you can take any number of steps. You can scale it by any real number. So let's write down maybe a lambda. Okay, so if you take this piece of instruction, okay, which is made up of two parts. First part is get to the line first. Second part is look in the direction and you can take any number of steps, any fraction, any decimal, any positive, negative number of steps. Then you will be able to visit the whole line. This is how you build the line equation, or how you build a line. Okay. Okay, so this is the other way to find the equation of a line. Next one. Length of projection. Okay, so now back to dot product. Dot product is talking about projections. Okay, the mosquito thing. Okay, so length of projection. Okay, what is the projection again? Right? Let's say projection. Okay, A dot B hat. What does that mean? So that's A, vector A, slap into the direction of vector B. Okay, so vector B hat, because it's the direction of vector B. If I slap it downwards, so down, 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 what I will get is I will collect this mosquito, right? Like this on my palm. The length of projection, okay, sorry. This is the projection. This is the projection, this squash mosquito. Okay. This is the projection. The length of projection is the length of this thing. If I measure the size of this mosquito, it's the length, okay, of projection. Okay. So how do we find the length of projection? Just project, then you take modulus. Because the projection can be either positive or negative. You just want the length, just take absolute value. Okay. So it's just like this. Projection, then modulus. Okay. This is just a bunch of ways to manipulate things, which I'll just write down here for you to see. But when we see specific questions, then we will see case by case, what do we need to do? Okay. But we need to know how to think of it first. So over here, find the length of projection of this vector onto this line. Again, vectors is a very visual subject, very visual topic. So let's draw the line. This line is L, is described by this equation. Okay. Okay. This equation, vector R equals to 1, 0, 0 plus lambda 2, 2, 1. Okay. Lambda in R is described by this equation. Okay. So I have a vector 1, 0, negative 1. This vector, I will just put it on the line. I let it sit on the line. Remember, vectors, you can move it around, right? So let's say for some reason, this line, let's say this vector is called vector AB. The points A and B may not lie on the line. Let's say points A here, B here. Vector AB is like this. It may not lie on the line, but I don't care. I can pull the vector onto the line. Okay, so you can move vectors anywhere you want. Okay, so I put a vector here, sit on the line. Now I'm going to squash it into the line. If I squash it into the line, I slap it into the line, it will collect here. I want the length of this squashed vector. So let's find that. How do we find that? First of all, I need to build my projection. What is the projection? The projection is vector, okay, dot direction, okay, not this direction vector. It's the direction of this vector. I only want the direction. I don't want the magnitude. I don't want the magnitude to mess up my, yeah, no, I've never talked about magnitude of this dotted line or this like palm. Okay, whenever we talk about projections, we only slap it into a certain direction, a certain surface. certain palm. Okay, I only want the direction. So what I do is I take that vector 2, 2, 1, and I find the unit vector in that direction. So I divide by its magnitude. So the vector, the mosquito, slept into the direction. Okay, I'm gonna label this. So this is the mosquito. Okay, slept. Okay, dot. Then this is the palm. Okay. Yeah, okay, disgusting analogy, but yeah. Now I want the length of this slept mosquito. So length, just put the modulus. Okay, so this gives us the length. Okay, measure the length. Okay, so this helps us measure the length of the mosquito that's squashed into my hand. So length of projection is equals to this. Just need to go and calculate this. How to calculate this? Let's just do it one time. The denominator is just 2 squared plus 1 squared. Okay, I'm not going to count that. The numerator is 1 times 2. So I'll just write down the workings. 1 times 2 plus 0 times 2 plus negative 1 times 1. Then I modulus the whole thing. Okay, then whatever that is the answer. Okay, I'm not going to count this. Okay, so we're done with length of projection. Okay, let's go on to the next one. Forgot to make the box. So the box is, there's no space. Okay, anyway, foot of perpendicular. I would say that of all the possible things you can solve for in vectors, lines, and planes, the most difficult is foot of perpendicular. And it's the one that you need to remember the steps. Okay, so please memorize this recipe. Okay, so this one must really memorize. So memorize this whole thing. Okay, memorize. Okay, so this is the unfortunate part that you have to memorize. Okay, so let's talk about the recipe. How do we find the foot of perpendicular from the point, from any point onto the line? Okay, let's draw a picture first, because again, vectors is a very visual subject. So line, I have a point. I want to find the foot of perpendicular. What that means is I want this point, think of it as the line is like the ground. The point is some rock in the air. The rock is going to fall straight down. So it's going to fall straight down and then cause a dent. This dent, the location of this dent is called the foot of perpendicular. Foot of perpendicular. Why is it so? Because this point will fall straight down, so perpendicular to the ground, and the foot is just where it lands, the dent. Okay, so foot of perpendicular. Okay, to find this, we need to first think of a few specific things, a few specific facts, properties, right? The first fact is that this foot of perpendicular lies on the line. Okay, very important. That's how you get started on this question. The foot of perpendicular lies on the line. Okay, because it lies on the line, you write down the line equation